This will be the lecture over chapter 16. This is going to be the last chapter that we cover here in this course, and it's going to be over radiation safety and protection. How do we go about establishing that a treatment is going to be safe? Not so much for, although to some degree, for the patient themselves, but also for those that happen to be going about their daily routines outside of where the treatment is going to be delivered. So, what are we looking at here? What is it that we have to review? Well, we have to look at the ionization and the production of charged particles, what's doing the ionization, what sort of quality do they carry with them, and the biologic damage potential. We have certain somatic effects, carcinogenesis, embryologic effects, cataractogenesis, lifespan shortening. We also have genetic effects such as mutations that we need to consider. So the different types of radiation that we have alpha particles, we have beta particles, and we have X-rays and gamma rays, all of which are going to have a certain quality factor assigned to them. If we look at alpha particles, we have a positive 2 charge, the atomic mass of 4, so that means we've got 2 neutrons and 2 protons. And so it gives it a positive 2 charge. The origin, of course, this is the nucleus of a helium atom. Beta particles, we have a negatron as well as a positron, and you can see the charges there. Also, they will be emanating from the nucleus. We have neutrinos, which are not going to carry any charge or atomic mass number with them. X-rays, which emanate from electron shells, and then gamma rays, which of course are emanating from the nucleus. These sources can be natural in nature, cosmic rays, or radiation from the ground, such as radon, radiation that is internal. We also have man-made radiation for medical procedures, consumer products, and other types of radiation, nuclear radiation. Exposure. It is a measure of the ionization that is caused by absorption of X-rays in a specified mass of air at the point of interest. This is the kind of thing that we've been talking about since well before in this chapter, or we've also been looking at it in previous chapters. And going from ionization to dose has been the step that has been taken in order for us to figure out exactly how to measure the radiation that has been introduced into the body. The conversion factor here, where 1 Rankine is equal to 2.581 times 10 to the minus 4th coulombs per kilogram. So this is how much charge is produced per kilogram of air. The absorbed dose is going to be the amount of energy transferred to the interacting medium per unit mass of the medium by ionizing radiation. So in other words, you're taking the step from here and saying, okay, how much kinetic energy ends up getting deposited per mass of the medium. In other words, how much ends up, eventually how much ends up in the human body. Units are going to be rad or gray. And the conversion factor here, 1 gray is equal to 100 rad, or 1 centigrade is equal to 1 rad. The equivalent dose, it's going to be the amount of biologic harm to tissue caused by exposure to ionizing radiation. So each different type of radiation is going to be given a quality factor based on the amount of biologic harm that it does. And this is going to account in several different categories. So X-rays, gamma rays, and electrons are going to be given a factor of 1. Thermal neutrons are going to be given a factor of 5. High energy photons are going to be given a factor of 10, and fast neutrons and alpha particles are going to be given a factor of 20. So again, the higher the factor here, the more damage they can do within the body. So the units here are going to be rem or sievert. So 1 sievert is going to be equal to 100 rem. So the effective dose is going to account for partial body irradiation or non-uniform irradiation of the whole body. So you can see the different types of factors here. This is more of a weighting. If you actually go to Con here, and let me back this up a little bit. Go back a little bit further. There we go. You can see a number of weighting factors here, and this is going to be primarily from this particular equation here. We have the dose equivalent, the effective dose equivalent is going to be the sum of the weighted dose equivalents for irradiated tissues or organs, where you've got the total dose equivalent is equal to the weighting factor for the tissue that it's in, and H sub T is going to be the mean dose equivalent received by that tissue. And it's going to be the proportionate risk of tissue when the body is irradiated uniformly. So these factors here are an assumption of full expression of the cancer risk and an assumption of population distribution over all ages and sexes. So it's a guess, but it's an attempt to sort of gauge what the total dose equivalent is going to be depending on where it is present. So what sort of stochastic effects are we looking at here? There's obviously they're random in nature. There's no particular threshold. That's only 0. There's only a 0 probability when there's absolutely no dose. If there's any dose present, yes, you have a chance of this actually occurring. And what we're referring to here is going to be the radiation-induced cancer. Non-stochastic effects are also going to be known as deterministic, and these do have a threshold. Doses below the threshold have 0 probability of causing this effect. However, if you're above the threshold, it's going to happen. One example of this is cataracts. If the lenses of the eyes go above a particular dose, then it's 100% guaranteed that you're going to start having cataracts or clouding of the lens. Genetic effects. Damage to the genetic material in the nucleus of the human cell is what we're going to be experiencing, or what the patient's going to be experiencing. Damage may not be apparent for many years or perhaps even generations. What can happen from that? Well, we can end up with genetic mutations. These can be spontaneous. These can be frequent depending on what is transpiring. And we are looking at base damage. We are looking at a single strand break. We are looking at double strand breaks. Again, these are breaks within the DNA. Or when we refer to base damage, we've got the base protein there, which could be damaged. And then we've got cross-linking, which can also happen. Basically, when you start having several different changes of the DNA, recombining in ways that is not normal, or something that the check mechanisms are going to have difficulty in trying to prevent or correct, these are the kinds of mutations that can happen. So again, what is radioactivity? This is going to be the emission of energy in the form of electromagnetic radiation or energetic particles. It's going to be measured in units of the Curie or the becquerel. The becquerel is going to be referred to as the number of disintegrations per second. And 1 Curie is just going to be a bigger unit, and it encapsulates or is equivalent to 3.7 times 10 to the 10th becquerels. So how do we go about measuring this? What's going to be the mechanism by which we go through and determine that we have a particular type of radiation or that we have a certain amount? So we've got to come up with instruments and devices designed to detect and or measure radiation. So we can do it through gas-filled chambers. We can do it through TLDs. We've also got neutron detectors in order to be able to determine what it is that we're dealing with. It's not as if we can actually see these things so we can determine what it is. We have to have ways in order to be able to interpret what's going on. So gas-filled chambers. These are chambers, obviously filled with gas, that become partially or fully ionized when radiation is present. They can measure either the rate of ionization or the level. And with an ion chamber, it is a gas-filled chamber that has an electrical charge applied to it across 2 electrodes. The electrical signal is amplified and displayed on a meter, and a properly calibrated ionization chamber is accurate within 2%, so they are suitable for measurement of radiation output of therapy equipment. So we got some ion chambers here. Gas-filled chambers, we've got the Geiger-Muller detector, where you can see here you've got a metal tube wall, which is a cathode, and then you've got the anode through here, and then the ionizing radiation comes through, and this causes an avalanche of particles that'll be attracted here, and they go through here and start setting off a sensor. And the voltage is increased significantly in order to be able to make the detection. And this is what it looks like. So TLDs, when exposed to radiation, it's going to store energy proportional to the amount of radiation to which it has been exposed. The energy is released as visible light when it is heated or annealed. When it's red, then it's zeroed at the same time and is ready to be issued again. So because of the small size, it is widely used in therapy. It's something you can carry around with you. Lithium fluoride crystals are used as TLDs because of the intentional impurities in the material. TLDs are not only used for personnel monitoring, but can be placed on the patient during treatment to measure the radiation dose in order to make sure you can detect how much they are receiving. TLDs can be stored after irradiation and read at a later time. So something we've all come to be familiar with are radiation dosimeters. Please do not leave them in your car. Radiation dosimeters are the most common personnel monitoring device utilized by the staff in a radiation therapy facility. So you've got the badge that you normally wear, and then you've got a ring badge, and here you can kind of see the inside. Neutron detectors. Neutrons are not detected by an ion chambers or the GM detectors. Neutrons have no charge and are non-ionizing. And they're not as easy to detect as X-rays. And the most common neutron detectors are the proportional gas type. So for radiation protection programs, the objectives are to document occupational and non-occupational dose equivalents, and to try to minimize them as low as reasonably achievable, or ALARA. So the responsibility for radiation protection, the administrative controls will mean that, basically, are there areas restricted for you to be able to go into? I've seen some clinics in which you have areas on the roof where you cannot go during treatment time because the shielding up there is not in place to be able to protect anybody. So they have limited access for people to go on the roof in order to be able to work on it. So those are ways in which the administration can try to protect those that still have a job that they need to do, but need to do it when they're not going to be hurt. So who's responsible for this? Well, radiation therapists can be responsible, radiation safety and protection officer, or the RSO. The facility in which the radiation is being administered. So what about the RSO? These are the people that provide the principles and practices for radiation protection. They have radioactivity measurements, standardization, monitoring techniques, and instruments. So in other words, they can go and they can measure and see what's going on and see if they need to freak out over something. Obviously, they're going to use math and calculate basic computations to use and to measure radioactivity. They're going to have an idea as to the biological effects of radiation, and the responsibilities are going to vary by the institution, however they've got that structured. So again, the ALARA principle is as low as reasonably achievable. Radiation safety principle for minimizing radiation doses and releases of radioactive materials by employing all reasonable methods. ALARA is not only a sound safety principle, but is a regulatory requirement for all radiation safety programs. So define reasonable. So basically it means minimizing the risk while understanding that the cost versus benefit for the dose reduction and knowing what that is. So what are typical ALARA levels? You've got quarterly action levels here for the whole body, the organ or an extremity, and the lens of the eye, and obviously for a fetus, which you definitely would like to protect at all costs since their cells are multiplying at a significant rate. Comparable risk, the National Council on Radiation Protection and Measurement, NCRP, has attempted to compare the risk of injury from ionizing radiation with the risk of injury in other occupations. And an occupation with a risk of accidental death of 1 per 10,000 per year is something that is considered to be safe. So you can see here the fatality rates for accidents in different occupations, such as trade, manufacturing, service, government, transportation, so on and so forth. So this is the number of workers that you have times obviously 1,000. And then the annual fatal accident rates per 10,000 workers, which you can see there. So NIRL, negligible individual risk level. It is a level of effective dose that can be dismissed as insignificant and below which further efforts to improve radiation protection are just simply not justified. So 0.001 rem or 0.01 millisieverts per year, where the risk of death is 1 in 10 million people. So the requirements for personnel monitoring Recommended for individuals for whom there is a reasonable probability of exceeding 25% of the occupational dose, or 12.5 millisieverts per year, 1.25 rem per year. Most hospital employees, including radiation workers, are lower than this level. And you want to protect your workers as much as possible, and trying to make a safe place is, dealing with this stuff is the best way to go about that. So the general rules of personnel monitors: never share badges or wear another person's badge. Do not intentionally expose badges to radiation. You don't, particularly, this is something that locums have to remember. Make sure you leave the badge there. Don't take it with you, particularly on an airplane going somewhere. That can lead to problems. Report accidental badge exposures or contaminations. Do not wear your badges when receiving a medical x-ray or other medical radiation treatment. Store badges in a safe place, and do not take badges to any other institution. In other words, we're wanting to make sure we're measuring where we are and not somewhere else. So the methods and types of personnel monitors. So active monitoring, where we have electronic dosimeters or pocket ionization chambers, or passive monitoring, where we have film badges, TLDs, and optically stimulated luminescent dosimeters. So the electronic dosimeters consist of a GM or semiconductor detector, electronic circuitry, display, and battery. The advantages here: relatively inexpensive, they're rugged, and easily reset. Pocket ionization chambers, quartz fiber electroscopes based on the same technology as the ionization chambers used to measure machine dose. And the advantages are real-time readings, and they're easily reset. Film badges. You've got radiographic film used to measure exposure, optical density. Anytime it comes to film, that's one of the things you have to worry about. The types, you've got a body, a ring, or a wrist badge. The advantages are they're cost-effective, convenient, dose is low. Film is really good at this. Dose as low as 10 millirem can be detected, and permanent record of an individual's dose. TLDs, they're based on the same technology as TLDs for machine output. And the information is destroyed when it is processed. So in other words, when you go through and you anneal that kind of stuff, then the information goes away. The advantages are reusable, they're very sensitive, and they can have extended wear. So again, you see the lithium fluoride crystals here, the aluminum foil and the planchet are here. Optically stimulated luminescent dosimeters. These are preloaded self-contained packet incorporating a thin strip of aluminum oxide. Advantages: they are not heat sensitive. They can be re-stimulated numerous times to confirm the accuracy of a radiation dose measurement. May be used for up to 1 year, and they are extremely accurate. I've never actually opened up one of these to see what's inside. That's probably a good thing. So other types of dosimeters: chemical. These are used by the military. Solution consists of alcohol-free chloroform and the dye bromocresol purple. When the chloroform absorbs radiation, hydrochloric acid is produced, which changes the dye color from purple to yellow. The records of accumulated dose, the purposes are to maintain a lifetime accumulated dose record, notify employees of monthly or quarterly dose levels, and monitor radiation safety practices of employees, and must be maintained indefinitely. You can sometimes see reports like this that are given to you for every quarter or perhaps for the year that sort of let you know what it is that you have been exposed to. So what is considered to be here the maximum permissible dose? Well, you've had an NCRP report number 17, which is the dose of ionizing radiation that, in light of present knowledge, is not expected to cause appreciable bodily injury to a person at any time during his lifetime. ICRP publication 6. So the permissible dose for an individual is a dose accumulated over a long period or resulting from a single exposure that, in light of present knowledge, carries a negligible probability of severe somatic or genetic injuries. Any effects of the dose that ensue more frequently are limited to minor effects that would not be considered unacceptable by the exposed individual and by competent medical authorities. So who establishes MPDE? You're looking at advisory committee on X-ray and radium protection, the Atomic Energy Commission, NRC, DOE, OSHA, and several others. So MPDE versus dose limits, occupational exposure versus non-occupational exposure. Radiation workers are going to accept risk of higher exposures. Radiation workers capable of consenting to higher exposure potential, and it's easier to track higher exposures in a smaller population. So the NCRP recommendations for occupational dose limits, you've got the whole body here and the annual limit in millirem, the organ or extremity, and the lenses of the eyes. The occupational dose limits from the NRC are listed here. It also includes a dose to the fetus. And you can see these recommendations are written out. This particular table is what I was given whenever I was going through school. The international origins of radiation protection, the Second International Congress of Radiology. So you've got the ICXRP, the ICRP, and the ICRU. So for protection in the United States, you have the ACXRP and the NCRP. So you have certain radiation protection organizations, UNSEER, you've got BEIR, ICRP, NCRP, the EPA, the NRC, and the Department of Energy. And you can see all of these listed here. So the ICRP, the mission is to establish, it was established to advance for the public benefit the science of radiologic protection, in particular by providing recommendations and guidance on all aspects of protection against ionizing radiation. And the activities are, it establishes recommendations, provides advice, and no jurisdiction to enforce its recommendations. So it's there to tell you, but it is not there to enforce. Now, the NCRP seeks to formulate and widely disseminate information, guidance, and recommendations on radiation protection and measurements which represent the consensus of the leading scientific thinking. There's a radiation protection watchdog and no jurisdiction to enforce its recommendations. The NRC is to regulate the nation's civilian use of byproduct, source, and special nuclear materials to ensure adequate protection of public health and safety, to promote the common defense and security, and to protect the environment. So it develops regulations, licenses users of nuclear materials, oversees operations of facilities using nuclear materials, and does conduct research. So the Health and Safety Act of 1981 established voluntary guidelines for states to follow in regulating healthcare personnel who perform radiologic procedures. State agencies, since we're located in Oklahoma, we'll go over that. The Oklahoma Department of Environmental Quality, the Land Protection Division, is involved in radiation management, and it's responsible for regulating radioactive materials, industrial analytical X-ray machines and particle accelerators, and medical therapeutic X-ray machines and particle accelerators. So regulations and recommendations. The NRC, we've got recommendations and regulations there, and current NCRP recommendations and or regulations as well. We have a whole list here of parts that go over different types of materials or activities that need to be regulated. You probably never even thought about all of that, but that's where they are. The NCRP report 102, equipment design and use, design, performance, and optical use of equipment recommendations, radiation protection surveys and personnel monitoring, simulators, therapy equipment, calibration guides, radiation protection surveys and working conditions, all of that kind of thing. All of those reports there. So if you need a cure for insomnia, you can go and grab those. 105 talks about the biological effects and protection against radiation. Regulatory control environments provides general information on radiation use in medicine. 107 addresses the implementation of ALARA for occupational exposure of persons working in medicine and dentistry. 114 describes the elements of Operation Radiation Safety Records Program. You got to keep records of what you're doing. 116, basic radiation protection, revised tissue and organ weighting factors, reviews absorbed dose, equivalent dose, radiation weighting factors, and effective dose. Addresses exposure in excess of the limits, limits for unusual occupations situations, guidance for emergency occupation exposure, and remedial action levels for naturally occurring radiation. Now, what are the cardinal principles of radiation protection? Time, distance, and shielding. So the less time an individual is exposed to radiation, the lower the dose will be. Increasing the distance from the source of radiation dramatically reduces the dose. And as a matter of fact, this is one of the best ways in order to be able to protect yourself. So because the inverse square law really does help you out considerably. So the further you are away, the more you're helping yourself by a squared factor. Shielding, most important of all radiation protection principles, and the fact that the more shielding you have between yourself and the source, the better off you are. So what do we use in the clinic? We use warning signs, lights, door interlocks, visual and oral communication, beam on monitors, and emergency off controls in case something gets out of hand. What are the warning signs? Entrances to radiation therapy rooms must be clearly marked with signs warning about the potential presence of radiation. Even if nothing is on, you need to have that there. Let's say the cleaning crew comes in or what's not, and you need to tell them, hey, be careful in this particular room. That's a good way to do it. Warning lights, beam on when that light is on. It means the machine is on. And near the control panel, the entrance to the room, the treatment machine do not necessarily indicate the presence of radiation. They're just saying that the beam is on. Door interlocks. Entrances to treatment rooms must be designed so the machine turns off or returns the source to a safe position if the door is open. Visual and oral communication, absolutely necessary for the therapist to be able to see and hear the patient throughout the treatment. If they start yelling, if they start moving or whatnot, you've got to be able to detect that. There's no ifs, ands, or buts about that. Leaded glass windows or closed circuit TV. It's a good way to do that. Beam on monitors indicate when radiation is present in the room. Indicator lights must be independent of the treatment machine. In other words, you can't have them depending on the same system. It's not going to work. These are capable of operating in the event of an electrical failure. Emergency off controls basically do not touch the big red button unless you need to, because that removes electrical power from the treatment machine, treatment room walls, treatment couch near the exit, and the control panel. I remember once there at OU, apparently some students were leaning up against the wall, and one of them hit the emergency stop button by accident, and that set them back by 30 minutes, and a lot of fun was had by all. Radiation surveys. The NRC defines radiation survey as the following. It's the evaluation of the radiation hazards accompanying the production, use, or existence of radioactive materials under a specific set of conditions. Such evaluation customarily includes a physical survey of the disposition of materials and equipment, measurements or estimates of the levels of radiation that may be involved, and a sufficient knowledge of processes affecting these materials to predict hazards resulting from expected or possible changes in materials or equipment. Contamination survey. Not a major concern for the radiation therapy department, primarily designed as a survey for laboratories using any unsealed radioactive materials. You might be thinking of perhaps the PET department. A wipe smear survey, a paper circle is rubbed with moderate pressure over a minimum surface area of 100 square centimeters. Each sample is analyzed for radioactivity, and then that result is documented. Equipment survey, radiographic and fluoroscopic equipment, gamma beam teletherapy equipment, leak testing used to test sealed radioactive sources. Radium sources should also check for radon leakage. Linear accelerators and frequency. At initial operation of such equipment, when any change is made in the installation that might change the radiation level to which a person could be exposed. Area survey, controlled or restricted area, any area to which access is controlled for the protection of individuals from exposure to radiation and radioactive materials. It's got to be clearly marked. Uncontrolled area, an area in which a person could not be exposed to radiation levels greater than 2 millirem in any 1 hour from external sources. So controlled areas are going to be areas in which, if you're thinking during an active clinic day where people are, sort of let through, patients are let in, a family is kept in a certain waiting area, that kind of thing. An uncontrolled area might be, say, a hallway or perhaps an elevator or something like that. It's close to a treatment area, but obviously we don't restrict who comes in and out. This is where the radiation protection rates need to be low. How low? Well, we're going to kind of get into that. So here are ways of letting people know that you've got areas here where you need to be cautious. So practical radiation protection, one way to do this, again, with shielding, is a barrier material. You've got primary shielding, secondary shielding, mazes and doors. You've got dose calculation factors for the use, the workload, occupancy, distance, and transmission. And then what type of barrier materials might you have? You've got different materials for different types of particles and different energies, major shielding materials, lead, steel, and concrete. This gets into concepts of a half value layer, which we have covered before. So it's the thickness of material necessary to reduce the dose or intensity of the beam to half the original value. And then you've got the 10th value layer, which is the thickness of material necessary to reduce the dose or intensity of the beam to 1/10 its original value. So here, what is the percentage of the original dose transmitted through a 3/2 value barrier? Let's see if we can draw this out. So if we've got a 3/2 value layer here, then the percentage, if we start off with 100%, which I'm going to attempt to draw this, and that is going to be multiplied by this raised to the 3rd power, because we have 3 of these here. That'd be 1/2 times 1/2 times 1/2. So that basically is 100% divided by 8. If you multiply all of that out, so that comes out to be 12.5%. That's supposed to be 12.5. Sorry about that. I'm going to clear that out. Let me see if I can actually do something that's a little bit better. Here at my old tablet here. See if this might make things a little bit easier to read. Let's see if I can find my stylus here. I thought it was around here somewhere else. Just a second. Okay, so now what about the second part here? What is the percentage of the original dose transmitted through a 2/10 value layer barrier? Well, let's see. Starting off with 100%, and that is going to be multiplied by 1/10 raised to the 2nd power. So that's going to be 100% times 1/100. That ends up equaling 1%. If a particular barrier in the therapy room is equivalent to 4 half value layers and 1/10 value layer, what percentage of the original radiation beam is transmitted? Well, let's say we start off with 100%. And that is multiplied by 1/2 raised to the 4th power. And that is then multiplied by 1/10. So that is basically 100% times 1/16 times 1/10. So that is the same as 100% over 160. And so 100% divided by this is, let's see, what does that turn out to be? That turns out to be, so if I take 100 divided by 160, so that is 0.625%. So not much. Not much at all. So let's take a look at this problem. The dose rate is 200 millirem per hour at a wall inside a room where a patient with a radioactive implant is being housed. If the dose rate on the other side of the wall cannot exceed 4 millirem per hour, what should the thickness of the wall be if 1/2 value layer is equal to 5 cm of concrete? Now, again, the half value layers and whatnot of particular materials are going to depend on the energy here. And there's no amount of concrete that's going to reduce this to 100%. So we got to draw a line somewhere. So Basically, what we are looking for here is something that's going to take, of course, I've got to do this. Let's see. We are looking to take 200 millirem per hour, and we're going to multiply that by some factor. And that is going to end up being 4 millirem per hour. Now, the factor is going to end up being 4 divided by 200, which is going to be 2 divided by 100, which is going to end up being 50. So we know here that that's going to be a little bit difficult in order for us to be able to present in half value layers, just simply because 1/2 is not the same as 150, but if I square it, that's going to end up being 1/4, which is not quite the same. So if I take 1/4 and multiply that by another half again, it's 1/8. If I take 1/8 and multiply it, that's 1/16. And if we are looking at 1/16, multiply that by another half, 1/32, that's still not 1/50th. So if I take 1/32 and multiply it by 1/2, that ends up with 1/64. So we're looking here, let's see, I've had 2 half value layers here. That's another third, a fourth, a fifth, somewhere between 5 and 6 is what we are looking at. So we're looking at somewhere between 5 times this particular value, and we're looking or somewhere between 5 and 6 times whatever this particular value happens to be. If you'll look over here, you can kind of see how I arrived at how many half value layers we're going to end up needing. Basically, if we're trying to cut this down to 4 millirem from 200, again, that factor has to be applied. So I take 4 divided by 200, which ends up being 2 divided by 100, or 1/50. So basically, I take 1/2 times raised to some power. I don't know what it is because I don't know how many half value layers I'm going to need. And that's going to end up equaling 1/50. If I take the natural log of both sides, I can bring that exponent down. So I've got x times the natural log of 1/2 is equal to the natural log of 1/50. Divide both sides by the natural log of 1/2. If you work this out, it ends up being 5.64 half value layers. So the thickness of the wall in this particular case is going to end up being 5.64 times 5. So it ends up being the thickness is about 28. Tell you what, let's try writing like a human being. Let's 28.2 cm. It's a lot of concrete, but make buildings to keep people safe. So there we go. So that's the example there on how to do that first part. Now, as far as the transmitted dose is concerned, that's going to involve with a little bit more computation than what I am interested in getting into right at this particular point. I'm going to be recording some problems a little bit later where we'll touch on that particular subject. Primary shielding is shields the primary beam, and that could either be internal lead housing or a portion of the treatment room designed to absorb the primary beam. The secondary shielding is going to shield leakage and scattered radiation and protects individuals occupying areas outside those areas of high doses. So again, controlled areas are going to be areas in which individuals exposed are monitored by a radiation safety program. Dose equivalent limit of 0.1 rem per week, or approximately 5 rem per year. Non-controlled areas, areas where the individuals exposed are not monitored by a radiation safety program. They're just passing through. A dose equivalent limit of 0.01 rem per week, which you can see the difference here. It's about 1/10 of what's going on there, or approximately 0.5 rem per year. Same thing here. Now, mazes and doors. This prevents leakage and scatter radiation from leaving the high dose area. The doors depend on the maze design. Most constructed of lead, 7 inches thick, and weighs up to 4,200 pounds. Now, dose calculation factors. We're going to be getting into a primary barrier equation here, where we've got the transmitted dose, which is the amount of centigrade per week. And again, if we're looking, let's go back to what I had here. What is a transmitted dose? This kind of thing is what we're going to be referring to, is the amount of centigrade per week, which up here, if we use that 5.64, then the transmitted dose here, we're looking at 200, or we're looking at 4 millirem per hour if we went with that 28.2 centimeters of concrete. If we went with more, then it would be knocked down even further. But for these particular factors that are listed here, we've got the transmission amount that actually comes through. We've got, or this is actually the amount that comes through. This would be this is the transmission without the other factors being added in. The workload, which we will see, the use, basically how, this is going to be the workload. It's going to be how much centigrade is delivered at the ISO center. If we're looking at a daily, we're going to be looking at how many patients we treat per day. If we're looking at it weekly, it's how many patients were treated, how many treatments were delivered throughout the week. The use is basically whatever room we're looking at is how often that room is used. The occupancy is basically how much time is actually the room being occupied. And then the distance is going to be measured in meters, and it's going to give us an idea as to how much of an effect the inverse square law is going to have on things. So again, for the use here, based off of NCRP recommendations, this factor ends up being 0.31 if we're looking at the floor. And the reason in a lot of cases is going to be if you're delivering APPA treatments, which happens more often than you might think, then anything that's aimed at the floor, that's going to happen more often. Same thing here with the ceiling, although not quite as much as the floor. The ceiling is also going to have more exposure. Now, each wall that may be struck by a primary beam, if we're looking at the sides, generally we're looking at a lower factor here. Again, the workload is going to be the total dose delivered to the ISO center per week. Treatments multiplied by the ISO center dose, and it's going to be the centigrade per week. The occupancy is going to be the exact occupancy determined by calculating the percentage of a 40-hour work week that the space is occupied. And then I talked about the distance and then the transmission, because no amount of thickness of barrier material is capable of fully attenuating photons. Some will pass through given dose outside the shielding. So depending on how much shielding we've got, we're going to have some transmission, but given all of these other factors, it may not be enough for us to say this is above the background of what anybody would receive in this particular area just by existing in the area, whether or not the machine is running or not. How do we estimate the occupancy? The occupancy is if a room is or area is going to be fully occupied, then we're going to give it a factor of 1. If we have partial occupancy, like a corridor, a staff restroom, employee lounge, or whatnot, then we're going to knock it down to about 0.2. If it's a hallway or a utility room, restrooms not used by occupationally exposed personnel, we're going to knock it down even further to 0.05. And if we're looking at stairways, automatic elevators, areas where pedestrians are or whatnot, we're going to knock it down even further than that to 0.025. But this is the equation that's going to end up being used for primary barriers. Now we've got some examples here of how we might go about and use that particular equation. I'm going to go through one of them. I'll go through some other examples here out of Khan so that we can have an idea also as to how to use that. So a 4 MV linear accelerator, or the energy that's being used at the time, is installed 3 meters from a 150 cm thick wall of concrete, separating the treatment room from an automatic elevator. Now, an automatic elevator here ought to clue in as far as what the occupancy might be. So the accelerator treats 150 patients per week with an average isocenter dose of 200 centigrade. So what is the transmitted dose to the elevator? Now I've come up here with a spreadsheet that kind of works all of this out. If you look at 150 centimeters thick of concrete, I have found some reports here that will detail, oops, wrong one, that will detail what some 10th value layers are of concrete. And we've got our energy here. We've got our concrete level here of about 35 centimeters or 30 centimeters, depending on how hardened the beam is. I'm just going to go with 30 because it's easy. You can easily divide 150 by 30. So if we say that the 10th value layer for concrete for 4 MV is 30 centimeters, we have 150 centimeters. So if I take 150 centimeters and divide it by 30, let's try this again. 50 divided by 30, I don't know why it does that. I've got 5 10th value layers. So basically I take 1/10 and raise it to the power of 5. This becomes my factor for B. The workload here is going to be 150 treatments multiplied by 200 centigrade. So that's going to be how much centigrade per week is actually being delivered at that particular point. The utilization here is going to be, this is going to be, the use factor is going to be applied against a wall. Now, since most elevators here are going to be going up and down, we're going to say that that is a side wall and that the factor there is going to be, it's not a floor or ceiling, so it's just going to be 0.21. Then the time here for the occupancy, I'm going to go with 0.025 because it's transient occupancy and it is 3 meters away. If you combine all of that, I'm going to multiply this factor by this factor by this factor by this factor, and I'm going to divide by the square of this particular number. That's going to end up giving us a transmitted dose of 0.000175 centigrade per week. For a non-controlled area, what are we looking to hit. We're looking for about 0.01 rem per week, which actually, if you look at a conversion of rem to centigrade here, it's a 1-to-1. So what we're looking at here is something that is much lower than what we're looking at for a dose equivalent limit. So that is pretty good. So let's go back here. So what is the minimum thickness of concrete necessary to keep the dose below the maximum level? Well, basically what you would end up with here is toying with this particular number to try to figure out exactly how many 10th value layers you would need in order for this to hit 0.01. I'm not really that interested in you guys completing that particular exercise, but that's what that would be. We've had other problems here, but I'm going to kind of go through what we'll have in Khan to discuss those problems. We'll do that here in just a bit. Brachytherapy. We have background information, basically what's emitted around us all the time. Storage of radioactive sources. We've got room design that goes into this, source preparation, radiation protection during patient care, radiation surveys, management of accidents. So there's a lot that goes into that. This is regulated by the NRC. They conduct licensing, radiation safety training, personnel monitoring. Those are all things either conducted by that or delegated to whomever would be responsible. For storage, basically eating, drinking, smoking, and application of cosmetics are going to be considered prohibited around this. Cannot be stored with food, drink, or personal items. I don't know why anybody would want to do that, but situations do exist, I suppose. Must be secure, must be clearly marked. Generally storage, we're looking at a hot lab. The equipment in the hot lab is a radiation survey meter, a well counter, a safe, and a storage for spent sources. Must be ventilated, lockable, warning signs posted, and adequately shielded. Something like this. For inventory, you take the date and time in which it was received or stored, the number and activity of sources removed, and then the number and activity of sources remaining, patient's name, destination, initials. Containers must be labeled and adequately shielded. Transportation never left unoccupied. You know what the route is, so if something goes wrong, you kind of know where it is, or at least how much was there, and you avoid exposing the general public. Room designs. Properly shielded rooms are not always available. Shielded hospital beds are uncomfortable and impractical, and nursing floor rooms add shielding to the door, perhaps have them located at the end of the hall, not on the first floor, to prevent people from walking by outside. You've got a large room to keep a greater distance between the patient and others, and a door interlock. Source preparation, you've got applicators or catheters or afterloading devices. You've got source preparation methods, and you've got cleaning applicators. For patient care, you've got no bed baths. You've got the minimum time spent with the patient. Housekeeping should be notified. Bandages must be surveyed before disposal. Linens must be surveyed before removal, and the patient should be confined to the bed. Radiation surveys, you want to do some leak testing and area and room surveys, transmission dose in patient room, hallways, adjacent rooms, and you want to survey after sources have been removed. Make sure you can account for everything.